Alright, time for another DraftScience video presentation. I'll get the mouse out of there. Yes, Christmas fun edition. Yeah, well, hell with that. Um, Nothing fun, on this planet. Nope, 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 not allowed. You must constantly fight through all the nonsense. So, two things. So we have one comment that just links again to the stack exchange, um, which, fine, okay. Uh, the other guy linked to that, and I just, was sort of pointing out, this is all convoluted mush. But anyway, we'll go through some of the convoluted mush. Um, and so then I found a page last night that has the original arguments that Leibniz was making, with the other intellectuals of the time. And, it's all veiled in their God talk and, all the other mush that's in there. Descartes and all those people. And, which is sort of depressing just because the context is just a bunch of religious kooks, pretending to be scientists. Which, it just doesn't look very good. But anyway, there's good science in it. I'm not dismissing that. But it all hinges on you have to find the point where, wow, did their logic go south? There's a point somewhere in the convoluted rationale where you can just find a little place where, whoops, that's your mistake. And that's sort of what they were arguing is these, fundamental, they come up with an experiment, right? Like the clay experiment or a lever. They start using levers, and start talking about time equations and forces and all this crap. And what a lever's doing. I mean, you can know it, I can know it, that it's just giving you more time to apply energy. All right, and that makes it possible for you to do a task because you break the task into little pieces, and you couldn't do it in the time that's required, just lifting something, in this much time, this much distance. Because the fact is gravity is fighting against you. The faster you try to lift something, the more gravity fights back. And that's funny that's the theme in here. So, I mean, that's one of the key ideas. Now, the other key idea is relativity, which is, to my advantage in a huge way. All right. I mean, I didn't realize I was going to be able to, crumble the foundations of relativity with this argument, but it really does just crumble it because that's part of the reason why this hooky fooky bullshit kinetic energy was invented, was to cover their asses for the fact that actually physical experiments do show relativity is horseshit. Okay, they actually do show it. They show you pretty obviously that it has to be horseshit. The example is things hitting each other. You can understand the dynamic, and the dynamic is actually going to show you that these two objects can't be in some relativistic space because the fact is the energy is in both of them. And it is going in both directions. And it's not just a matter of a bullet hitting a brick wall or a brick wall moving towards a bullet. Those two events will be different, and they will tell you which one is happening. You will be able to tell the difference between two things that are moving into each other and when one thing is crashing into the other. So this is, I probably should draw this stuff. And it gets to the whole essence of understanding what the hell energy is. I'm arguing it's real stuff. And so you understand it as little bits of force that you're going to collect. Little bits of energy. It's fish. It's stuff. Energy isn't nothing. It's a something. And you collect it. All right, so the simple argument is okay. So here's I didn't really want to do the relativistic argument first, but we're sort of stuck with that. So you have two scenarios, okay, two bullets, and so the relativistic argument is you can't tell which one is moving. All we know is that we're going to have an interaction between two bullets that's going to equal, a doubling of velocity. So either this one's going to x speed and this one's going 2x speed, or this one's going 1x and this one's going 1x. Now you can sort of understand, I think you can understand, that no matter what you're doing, what's going to happen when they interact. Okay, so if if you interact with something, so let's just say the bullet's just going to hit a brick wall, and we're just going to decide whether the wall's moving or the bullet's moving. What's going to happen is there's a real momentum error. Okay, I mean, it's really going this way, let's say. And if it's really going this way, this is the 2x now. So all the energy is in the bullet. The only way this fights back is through reflections, right? This energy has to hit this and it has to reflect back. That's the only way this fights back. Now, if this was moving, you can sort of understand that then it's direct force against direct force. And you sort of understand that reflections are going to be a lot weaker, okay, than direct force. So I'm actually moving two things into each other, two equal things, and they're both going the same speed. Okay, so I have two equal things, both going one speed. All right, you can sort of understand that all of their vectors start off as force, and then they'll start reflecting back at each other, right? I mean, this force will come into this, hit a particle here, bounce back, and hit this one again, right? And the same thing's going to happen here. And in a sense, what's going to happen is that energy is going to get trapped going back and forth, and like a paramecium, you can take a paramecium, little living thing, and you can put them in a trap, right? You put them in a trap, and it has a hole in it, and the paramecium will bounce, and it'll finally pop out, right? Well, that's what the energy is going to do. The energy is stuck, and it's going to get more and more intense as it's bouncing back and forth, and it's kind of going to sit there and just eventually force the energy to go in a direction it can escape in. So you can just sort of understanding it. It's just bouncing and bouncing. And as soon as it finds a weak spot, as soon as it finds a place where there's less pressure, it's going to zoom. Okay, and it's sort of like water waves. Water's uncompressible. You push it this way, forward. And what happens is you create this huge amount of pressure because it's uncompressible, and the water ends up going up because that's the only direction allowed it. You've created huge pressure going this way and this way. It can't go down because that's the ground. So where does it go? It goes to the soft spot. It goes up. And then gravity pushes it back down, of course. So you can understand that this is probably a real testable thing in the sense that you can sort of establish that this can't be going zero velocity because the only energy we might see is reflections then. There's no direct contact. So there's going to be a lot less of this deformation. If they're both hitting each other, you're going to have more deformation because you have more direct contact between the energy. And if one is actually stationary and the other one's moving twice as fast, so this one's moving twice as fast and this has no energy, well then this one can only reflect energy. That's all it's got is reflections, and reflections are going to be slower and weaker. So that's all it's got. So this one's going to win. No doubt about it. These two things aren't going to stay where they are and all the energy go this way. So if one of them's actually moving, okay, the one actually moving is going to reveal the truth. So this was what's in Leibniz was a relativist. I didn't know there were relativists 200 years ago. I mean, kind of hard relativists. So, I thought Einstein invented this horseshit, and really it was invented a long time ago. So that is sort of just the mystique of Einstein, that he invented relativity. A whole pile of these loop-de-doos were relativists. And so he was trying to defend relativity. And that's really what all this, that's where that's where all this bullshit fake energy came from. Is an irrational defense of a silly theory. All right, so this is just so basic. So the other error, I guess I'll get to that, is so you can sort of understand that if I did have a substance, all right, and you came at it with two different bullets of different speeds. So this one's going twice as fast, 2 velocity, and this one's going in slower, 1 velocity. You can rationally understand that this thing isn't going to fight these two bullets equally. Even though it's the same substance, right? You could even think of this as being gravity. But gravity, most of the matter is like gravity. It's going to do something, okay? You think gravity is the same rain coming down. Well, no, if you're moving into the rain, you're going to get hit by a lot more rain. So obviously the one going twice as fast into the matter, you can understand that per second, it's going to interact with a lot more atoms, right? I mean, it's going faster. So it means it has to be interacting with twice as many atoms than this one, right? You know, something like twice as many, right? I mean, we're just doing an average here. I mean, obviously other factors, you know, how much the stuff goes this way or that way is going to affect it, all kinds of other factors. But I'm just saying as a clean example, you can understand if it's going twice as fast into the matter, it's going to hit twice as much matter in the same amount of time as this other bullet. So clearly the stopping force is not equal. This isn't going to fight back with exactly the same amount of energy. See, their argument, their rationalization is to say, oh no, it fights back with the same amount of energy. They think gravity fights back with the same amount of energy. So this is where we go back to Newton and how Newton already answered all these questions. So, you know, here we have a pendulum and we're swinging the pendulum, blah, blah, blah. Right? You can see that, right? Well, it's not very illustrative. I'll put some arrows on here. And so what Newton told you, what Newton observed, which is sort of curious and interesting, I should put those on the same arc, is that if I just swing the pendulum this little tiny bit, right, or I swing it this big bit, the period, the amount of time it takes will be the same, okay? So this little tiny distance, it takes the same amount of time to stop this. So you understand, this has a very slow velocity. And when I let go of this one, it gets very little velocity. Its maximum velocity here is really tiny. Okay, but it takes just as long for it to swing as this thing, which you can say, well, you know, if this is a heavy weight, I can have a huge velocity. Okay, by the time it gets here, it's a huge velocity. But it's going to stop in exactly the same amount of time as this is going to stop. So we already know that gravity doesn't apply an equal amount of force constantly. There's not a constant amount of gravity kind of argument. And there is in the sense it's a constant rain. It's a constant amount of matter. Gravity is matter in a sense, right? I'm saying it's force, but force has mass, it has momentum. So it's an object, just like any other object. If you move into the object faster, you're going to hit more of the object, right? So if I'm moving twice as fast into the object, I'm going to hit more of the object. So obviously gravity isn't applying an equal force when you're moving into it. It's fighting back just as fast as you're fighting against it. It applies more pressure to you. So the faster you go into gravity, the more gravity is going to push you back the other way. You're going to interact with more gravity. So gravity really can be understood as a substance, as stuff. I'm obviously saying it's stuff moving, but regardless, it's a net amount of stuff moving, right? There's more stuff coming down because the Earth ate up a bunch of energy moving matter around. Energy. Okay, yeah, it didn't get anywhere. See, this is another thing that's just so irritating about their physics. They think work is what you accomplish, right? So when you go to work, if you don't get anything done, like your computer's down and you just sit there and eat bananas, you didn't go to work. You didn't do any work, right? Because work is about accomplishment. Work isn't about what you do, how much energy you expend. So that's, you know, just part of the silliness of this whole conversation is they don't even understand what work is. Work is having to drive to work. Work is having to stick your card in the machine, go boom. You know, that's work. Work is the whole process of going to work. Whether you accomplish something or not, who cares? That's not the work part. That's not the part that required you to eat a good breakfast and eat your Wheaties. Anyway. So, I mean, physics already can't get these simple concepts right. That energy, you can expend a lot of energy and accomplish nothing. That can happen. I can move this back and forth, okay? Now, by physics standard, right, all that's going to matter is where did I stop. So if I started here and I end here, I didn't do any work. Now, if I start here, okay, and I end here, well, I did a little tiny bit of work. I mean, that's how they look at things, and it's just the wrong way to see it. The energy and work aren't the same thing. It's just silly to call them the same thing. It's silly to draw an equal sign between them. Because what we're really, the real argument is what really took place as interactions and how much of this stuff exchanged with each other. All right, so let's see if I need another argument here. So anyway, so I'm just saying there's explicit argument. Now even modern day guys are making these arguments where they're not even conceding Newton's argument. So they're pretending not only that gravity doesn't actually do this, which is just a fact that should be written in stone, okay, that gravity fights back proportional to your velocity. Gravity does not apply an equal force. It applies a force proportional to your velocity against it. So the more you fight it, the more it pushes against you. And the more you're going with it, the less it pushes with you. So, I mean, that's just a fact. So, they think, oh, yeah, it takes more energy to move something. No, it doesn't take more energy. It's just if you're running away from the energy, yeah, it's not going to be as effective. Okay, gravity can't work on you if you're moving in the same direction as gravity. Gravity is going to be a little weaker. Okay, but if you're moving against it, gravity is going to be a little stronger in the sense you're going to hit more of it. So that's just a basic thing. Newton already proved that, so we're done with those kind of things. We already know that intuition says one thing. Intuition says this has to take a lot longer than this. So intuition is wrong. The truth is, no. The system fights back proportionally. All right, the time is exactly the same. There's more force pushing it, obviously. It's just kind of obvious. Gravity's pushing back harder here than it's pushing back here. You run into more of it, okay, because you have a faster velocity. You've moved into it quicker. If I move into the matter quicker, I'm going to hit more matter. The faster I move into it, the more matter I'm going to hit. I'm going to interact with more energy reflecting back at me, and I'm going to be slowed down faster. Fact. Faster than even. Faster than always the same. It's not going to be always the same. The faster I go in, the more energy I encounter per second. The slower I go in, the less energy I encounter per second. So I guess I'll just read the key little bits and let's see how it goes. All right. So let's do this guy's comment first. So I'm just going to read the first paragraph because the rest is a stall. All right. This has been one of those questions that I've asked in my physics class to myself. Why is momentum not directly considered energy and instead we've KE? For all purposes of theoretical considerations involving notions of energy, I do think about it in terms of momentum, right? It's just logical. Oh, anyway, when you have a mass with a given velocity, that is all the energy kinetic it is exhibiting. MV as energy is simple and rather elegant to form pictures around, and there is in here no need for squaring. There's no need to complicate it. I mean, it's just basically telling you that energy is like a substance. You have a certain amount of it. Okay, whether you call it a horsepower or a watt or whatever you call it, it's a certain amount of little bits of stuff. I don't care whether you call it bits, in a direction. And that's all it is. It's extra stuff in a direction. And that extra stuff can never be killed. Now you can change which direction it's going, but you can't kill it. You can't get rid of it. You can't destroy it. It always has to go somewhere. And you have to account for where it goes. And it's just not that complicated. All right. Now, if you take the mass velocity applied over a time frame, so this is probably where I'll leave this part, just because, again, this is really, we're not talking about that, though. We're not talking about how much energy or force it takes to acquire the energy. None of that stuff has anything to do with what something has. And even talking about potential energy is such a cheat. I mean, doing these stupid conversations about, conservation of energy when something literally isn't moving. You know, I mean, it has no momentum. It's just in gravity. I'm holding something up, and you're going to say, oh, it has potential energy. It really doesn't have anything. Okay, all right? It's just in a place in space. And now the energy in the space can work on it. But it doesn't have anything. All right. So that's where this all kind of goes south, is when they start applying, assuming that things can do that. All right, so this is where so there's two different guys answering the question here. So, and I'll just do this little part because this is the only part you really need. Now we apply a constant force. So we have two things moving, and now we're going to apply the force to stop them. To slow both objects down to a standstill. So you have two objects moving, one's twice as heavy or one's twice as fast. Doesn't really matter which way you do it. From F delta T equals delta P. Okay. It follows that the time needed for B to slow down is twice as much. We apply the same force to A and B. So again, none of these interactions will the same force be applied to things moving two different speeds. You can understand that they're not going to interact with the matter at the same amount of pushback. I can't possibly have the same amount of pushback when I'm hitting twice as much matter per second. So I mean, that premise right there, we apply the same force to A and B. So we know right now, nothing does that. Gravity doesn't do it. Substances don't do it. There's no way to make that make any sense at all. In no circumstance where the same amount of counter force or resistance be applied to things moving at two different speeds. The one moving faster has to be hitting more matter, and it has to hit more force. So it's right there. That's where the logic is broken, because now he's going to force the world to be that way. And so now he's going to say the thing going faster takes 4 times the time to stop. Well, of course, if the thing you just shot it into can't apply force proportional to its mass, force proportional to its density, force proportional to the fact that it's a real thing, not an imaginary thing. Imaginary things can apply the same force to two different things coming into them. I mean, I could make an imaginary thing that could say, oh, I can only push back the same amount for both of you bullets. So even though you're going faster, I'm going to pretend to disappear so you don't hit very much of me. So I'm going to treat you different. Somehow the matter's going to say, I know you're going faster, so I'll get my atoms out of the way so you can't hit them. I'll rain on you less. You know, like gravity's going to say, because you're going faster, I'll rain on you less. That's the logic there. So obviously, you know, this answer, dead, silly, stupid. We apply the same force to A and B. There, right there. Therefore, the braking distance for B will be a factor of 4 times bigger than the braking distance for A. Right. And it's completely irrational. No system does that. Only a system designed to pretend, okay, to apply some kind of even force could do that. No natural system does that. No, I mean beyond, like I said, the resistance of clay. Clay's resistance to deformation and blah, 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 blah. Yes, clay has a bias towards fast things. Anyway, a bias allowing fast things to interact with less matter. Okay, so the other explanation is the relativity one. And that's the one everybody says is the good answer. Yeah, the completely silly one. All right. That the energy in a constant gravitational field is proportional to the height is established by statistics. So let's understand, no, the exact opposite is established by statistics in the sense obviously gravity fights back. Okay, if you believe the law of the lever, an object will be in equilibrium with another object on the lever when the distances are inversely proportional to the masses. So again, they're playing games, you know, where we know you're just changing the amount of time over which you're applying a force. Okay, so you're making it easier by basically making the matter lighter, only affecting some of it at a time. So you're basically, in the case of the lever with gravity, you're basically just saying, I'm going to slow down the lifting process. And so I only have to add a certain little amount of energy per unit of time and make the job seem easier, like I use less energy. I'll use the same amount of energy, and I'm just doing the convenient thing of applying it slower because that's easier on my joints and my muscles. Okay. This allows you to lift objects and lower them with very little effort. Okay, this isn't where's the relativity part. Another way of saying the same thing uses an elevator consisting of two platforms connected with a chain and a pulley. Okay, so this is just establishing that twice the weight is half the velocity, blah, blah, blah. So these are all things that's pretty uncontestable. This establishes that all reversible motions of the elevator, the ones that do not require you to do any work. So here we go, both in the colloquial sense and the physics sense. They're just broken the word work. So we don't know what is meant here. The mass times the height summed over all objects is conserved. The energy can now be defined as a quantity of motion which is conserved when the objects are allowed to move with a non-infinitesimal velocity. As Feynman's version of Archimedes. Well, anyway. Let's get to the other part that matters. This original, okay, here we go. This is the original, so yeah, Huygens was in on this whole conversation also. This is the original demonstration of the laws of elastic collisions by Christian Huygens. So again, elastic is just rubbish talk because there's no hard consistency. It's just about how you transfer the energy. It's how things interact. Is there a place for the energy to go, or isn't there? And that's all this is really about. Who argued that if you drop two masses on pendulums and let them collide, their center of mass has to go up to the same height. If you catch the balls at their maximum point, from this Huygens generalized the law of conservation of potential implicit in Archimedes to derive the law of conservation of square velocity and elastic collision. So again, that's just basically Newton's cradle again, so nothing surprising here. Okay, so you put the energy in, you get the same energy back out. This principle that the center of mass cannot be raised by dynamic collisions in the first statement of conservation of energy. Let's get to I'm sorry, I thought it was in here. All right, for completeness, the fact that an object accelerates at a constant gravitational field with uniform acceleration. So here's the problem right there, right? For completeness, the fact that an object accelerates in a constant gravitational field with uniform acceleration is a consequence of Galilean invariance. No, it isn't. It's a consequence of the function of gravity. And again, we're not talking about how fast gravity accelerates an object. We're talking about whether gravity fights back like any other material object. The faster you go into it, the more of it you interact with. That's the simple argument, okay? That's all you need to understand here. Do you believe that the faster you go into something, the more of it you will interact with? Do you understand that simple concept? Because if you understand that simple concept, you know why you don't need this squared velocity nonsense. And the assumption that the gravitational field is frame invariant and uniform motions up and down with a steady velocity. So here we go, up and down with a steady velocity. It's fighting back and it's weakening as you're going in the direction of it. So as you move with the flow of gravity, gravity has less effect. You move against it, it has more effect. Once you know that motion is constant, motion in constant gravity is constant acceleration. So that's the false premise. It's obviously, deceleration is the same as acceleration. Obviously, you could argue, okay, that gravity is decelerating you, causing acceleration in the opposite direction as fast as you move into it. So the faster you move into it, the more force it pushes against you. That's the premise they blew up right here. All right, so let's, this guy has a whole clay thing in here, so I guess I have to go further up. Previous answer related problem with work and die. Okay, this was the wrong guy. No, it was the right one. Okay, it's in here somewhere. He does this whole clay analysis. Okay. Kinetic energy. I don't know why they put this E, then MV. It doesn't even make any sense. Okay, so it's a ball of clay with a mass M moving with velocity V and amount of calories of heat and it smacks into the wall. Okay, the definition does not make reference to any mechanical quantity, and it can be determined using thermometers. So this is just a simple argument. There's a certain amount of energy. You'll create a certain amount of heat when you have two pieces of clay crash into each other. Okay, I will show that assuming Galilean invariance, so more of this nonsense where we have to put E's outside of V's, must be the square of the velocity. Okay, so so E, I don't even know what that means, frankly. It's just silly. It shouldn't even be there. It's the MV is all you're talking about is mass and velocity. That's all there are here. Okay, must be proportional to mass because you can smack two clay balls side by side and get twice the heating. So if I give both of them velocities, then I'll get twice as much heating. Give one velocity, one amount of heating. Okay. So further, if you smack two identical clay balls of mass m moving with velocity v head on into each other, both balls stop by symmetry. We know that both balls stop, okay, because their energy can't get through each other. So, and they're both pushing on each other with the same amount of force. So, I mean, this clay ball is going to push on this one, but this one at the same time is pushing against it equally. So obviously they both can't go anywhere because they both have equal amounts of pushing bits. All right. But now look at this in a train which is moving along with one of the balls before the collision. So now we're going to pretend relativity fixes something or breaks something. In this frame of reference, the first ball starts out stopped. So they're in a train, and now, but the experiment was pre-set up, so you're not going to have motion relative. You're saying you're looking at it essentially from a train. I don't know how well, anyway. So we're just going to change the scenario. We're going to say it's possible that the Earth is moving this way. When I did the Earth is moving this way at exactly the same speed as one of the clay balls, right? So that means the other one is moving twice as fast relatively, okay, because it's moving against the movement of the Earth. So one ball's not moving technically, and the other ball is moving twice as fast. So we're back to what I drew in just pointing out that, well, now the interaction means that one clay ball cannot possibly, okay, fight back as well because it's not moving. It doesn't have any energy moving. So the only thing it can do is resist. So that's all it's got. It doesn't have any aggressive soldiers. It just has defensive players, right? It can stop goals, but it can't make a goal. I don't know how to... And those are obviously two very different circumstances. There's no denying that if you're going to believe in this relativity stuff, that somehow you have to deal with that fact that there now will not be energy against energy. There's just going to be energy against reflected energy. All right. But now look at this train which is moving along. Okay, in this frame of reference, the first ball starts out stopped, and the second ball hits it at 2v, and the two balls stuck system ends up moving with velocity v. So the argument is that because one of them's moving and one of them's not, you're not going to have this equal force, this balance. So now the whole clay thing is going to move off. So it's going to be really different circumstance. Okay, they're not going to cancel each other out, and the whole system is going to move in a direction. Now the problem with that is you already, well, he'll say it. All right. The kinetic energy of the second ball is E, whatever this crap, I don't even know, this notation is so retarded. At the start point and and after the collision, you have 2 MeV, kinetic energy stored in the combined ball. All you have is a certain amount of momentum. So that's it. But the heating generated by the collision is the same as in the earlier case. So this is the joke part, right? Because what they're going to say is that the deformation, you have to pretend that both events happened. That the two balls actually hit each other, deformed, all the energy went sideways, and that somehow, no, one ball hit the other ball, the clay, there wasn't as much deformation, and it all moved off to the left at half the speed, at the velocity of one of them. So there was half deformation and half motion. And you have to believe that both of those things happened. So that's where relativity just completely breaks, because both of them didn't happen. One of them's explicitly it's going to be true. Either there's going to be 2x deformation, or there's going to be 1x deformation and motion in a direction. And those two outcomes are completely different, and they completely tell you that relativity is horseshit, because both things can't happen. Only one of those things happened. So we'll know that either they're both moving, or one of them's moving and faster and one of them's moving slower. That they don't have equal velocities. The fact that they don't have equal velocities will be revealed in how they interact and how they deform. So the deformation will be evidence of the fact that there was only one frame. It's the universe's frame, and the event happened in the universe by the universe's rules. One of them actually had momentum and the other one actually didn't, or they both had momentum. And you'll see the difference. They won't look the same. This is another experiment you can do in your spaceship, and you will be able to see the difference of the physics. So in spite of the fact they say you can't do any experiment, there's every indication that if you do these experiments carefully, they'll tell you the truth. Okay, so do them carefully and they'll tell you the truth. Because there's a real difference between interacting with something that has momentum and interacting with your energy reflected off them. The reflected energy is different than the energy. The reflected energy, you can logically kind of understand, has to be something less than half of the... It has to start, let's even say, it's really time dependent, right? Because it doesn't really get strong until you get closer and closer and closer. If you're depending on reflections, the reflections are moving back and forth. So you're both getting pushed by the reflections. Obviously, the reflections get intense when you get really, really close to each other. You're both getting pushed really, with a lot of energy. And that's why there's deformation. All right, anyway. Okay, so I'm satisfied enough going with those two things, and again, I found a page that I linked on his comment. I'll leave a link below. It's kind of an interesting, where they're using the actual text of Leibniz and the other guy. That's not it. Here, no, here. Yeah, this is it. All right, so it's pretty well written. I mean, a guy's just comparing the arguments made by the different Descartes. See my computer's happy moment. Let it last. Well, it's okay, computer. Tell me now. You're coming back. Okay. Yeah, I was just seeing what I could get away with. Obviously, I'm not getting away with it because sync is way off. So I just get out of here. So, till the next time and such. Hopefully.